Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the 7th video in the series on Smith charts and the second on the how-to part of the series. In the last video, I showed you how to use a Smith chart to design a series stub match using a shorted stub. In this second of the how-to videos, I will be showing you how to use a Smith chart to design a parallel stub match with an open stub. Now, if you've already watched the previous video in this series on designing the series stub match with a shorted stub, that was video number 6, there will be some repetition here for you. I have to assume that the person watching this video has only watched this video, and I cannot leave any essential information out of either of them. Now, if you find this video helpful, please click on the like and subscribe to this channel. Now, let's begin the process of designing our stub match by answering the question, what is a parallel stub match? So what is a parallel stub match? Well, let's start with the assumption that we have a bad load over here. He's very unhappy, his SWR is high. And the fact that his SWR is high tells us that his impedance is not what it ought to be. If we could get his impedance in line, then the SWR would come in line too. In short, a stub match works in two-step process, summed up in 2 words, transform and eliminate. First, we want to transform the unwanted or imperfect impedance into something that we want. Now, as I said in the 3rd video in this series, while the SWR remains constant as you move along a transmission line, the makeup of that impedance changes. Now, these changes in the makeup of the impedance do so in such a way that the reflection coefficient and thus the SWR never changes. The same kind of transformation takes place with admittance as you move along a transmission line. Instead of talking about a 50 ohm characteristic impedance, we would talk about a characteristic admittance of 0.02 mhos. Now, in this video, we're talking about a parallel stub match, meaning that the impedance of the stub is applied in parallel with the transmission line. In the 2nd video in this series, I talked about parallel impedances and how we add the associated admittances and then convert them back to impedance to get at the total impedance. The easiest way to design a parallel stub is to convert our input impedance to admittance and then operate in the admittance realm to calculate our stub. The good news is the Smith chart makes this incredibly easy as drawing a line. Now, somewhere along the way as we move along the transmission line, the purely conductive or the real part of the admittance will be transformed into our magical characteristic admittance that we want, and in many cases that would be 0.02 mhos. Now, if we could know exactly how much transmission line we need to get to this point, then we have transformed our admittance to the place where the real part is what we want. The problem is the reactive portion of that is what is maintaining our bad SWR at that point. This introduces the need to eliminate. In the 2nd video in this series, I addressed the issue of eliminating the reactive portion of an impedance. This same principle applies to admittances. This is where the stub steps in. The stub introduces an opposing reactive component right at this point to eliminate the reactive component of the admittance that is being presented here. And what are we left with? The purely conductive real portion, and everything is great and we have a wonderful SWR. Well, how does this stub do this? Well, in the case that we're talking about here, we're going to be using an open stub, and the admittance is 0 plus J0. Now, just like any transmission line, you have an open end over here, and you're moving along the transmission line, and the makeup of that admittance is going to be changing along that transmission line. So if we could pick just the right amount of transmission line between the end, that open end, and the other end that's connected up here, we could get just the right amount of a reactive component to oppose this reactive component and eliminate the reactive component of this impedance, of this admittance, and then get what we want over here. Now, how is it built? Well, with a parallel stub match, well, the stub is put in parallel with your transmission line. It makes it pretty easy to implement. You could implement it using just a simple T connector like this one, with your stub hanging off of one side and your transformation over here and off to your transmitter over here. So let's go into the actual method of figuring out what you need to make this work using a Smith chart. The first and most important step in this process is knowing the actual impedance of the load. Now, the best way to do this is to measure it with a properly calibrated VNA, or a reliable and accurate antenna analyzer. Now, don't forget, it must be done right at the load's connector. Any distance at all away from the connector, whether it be a piece of coax or an adapter or any other such thing, will affect the measured impedance. The second one is to know your coax. You need to select your coax and determine what its velocity factor is and know what its characteristic impedance is. Well, you might say something like, well, I have this RG8U coax here, and because I know it's RG8U, that means it has a velocity factor of 66% and a characteristic impedance of 50 ohms. Well, I wouldn't bet on that fact. In fact, here is a table of various versions of RG8U type coax. Notice the different velocity factors. Here we have one a velocity factor of 66%, one of 78%, one of 84%. And notice too, the nominal impedance here is 52, 50, and 50. And they're all touted as being RG8/U type coax. And this is just one manufacturer. I strongly suggest that you measure the velocity factor of your coax using one of the methods that I cover in my video series on velocity factor. The data sheet may say 66%, but you might measure 64. And you say, well, that's not much of a difference. Well, actually, it can be. In a stub match I created for video number 8 in this series, which operates at 100 megahertz, this made a difference of over a half an inch, which can be huge, leading to less than desirable results. And again, regarding characteristic impedance, we usually assume 50 ohms. It's kind of a standard industry-wide, but you notice that they're not all necessarily 50 ohms. Take the time to know your components, and this will save you a lot of frustration down the road. Okay, so now let's begin our paper and pencil exercise on the Smith chart to create a parallel stub match with an open stub. For the sake of this pencil and paper exercise, I have chosen the frequency of interest of 146 megahertz. The load impedance is going to equal 11.65 minus J8, which gives us an SWR of 4.44 to 1. Now, the coax that we're going to use in this little exercise has a velocity factor that has been measured at 67% and a characteristic impedance of 50 ohms. Now, as I said in the Smith chart tour video, video number 5 of this series, the values on the Smith chart are all normalized values. So, the first step is to normalize the impedance of the load. So our impedance is 11.65 minus J8 with a characteristic impedance of 50 ohms. So we take the 11.65 and we divide that by 50, we get 0.233. We take the 8, we divide that by 50, and that gives us 0.16. So our normalized impedance is 0.233 plus J 0.16. All right, now we have our normalized impedance. We can plot this on our Smith chart. The first step is to locate the real or resistive circle, the 0.23 circle. So here we have 0.1, 0.2. Get out your calibrated eyeball, folks. Here is 0.22, 0.24. So right about in there is 0.23. And so our 0.23 circle is this nice red circle here. Second, we need to locate the minus J 0.16 circle. Now, right off the bat, we notice that this is a negative sign out in front, which tells us it has to be in the southern hemisphere. And then we locate 0.16. So go out onto the outer edge. We have 0, we have 0.1, 0.2, 0.11, 12, 13, 14, 15, 16. So this pretty blue line here is the minus J 0.16 line. Next, we place a dot where the real and the imaginary, the resistive and the reactive cross. That is our impedance. The next step is to draw our SWR circle. So we take our compass, we stick the pointy part here, we got the pencil part right on our dot here, and we draw this circle all the way around like this. This is the SWR circle. Anywhere on this circle, the SWR remains the same. However, the makeup of the impedance changes. Because we are talking about a parallel stub, we want to operate in the admittance realm, so we have to convert our impedance to admittance. Well, this is very easily done with the Smith chart, as easy as drawing a line. To do this, we draw a line starting here at our impedance. We proceed through the center and continue all the way through to the outer edge over here. The next step is to put a dot where this line crosses the SWR circle. It is exactly at this spot that our admittance lay. So now we read the admittance from that dot. We locate the real circle, which is this red one here. We locate the reactive, which is this one here. And we see right here, we have a 3.0 circle and a 2.0 circle. So Y, or the admittance of the load, is 3.0 plus J 2.0. And we know it's a plus because we're in the northern hemisphere of the Smith chart. Next, we want to read the wavelength value off of the outside ring here, because this locates us into the wavelength realm. And so we look along the edge here. We have 0.21, 0.22, 23. We have 22, 222, 224, 226. So we can see here that our wavelength of the load is 0.224 wavelengths. The second dot we plotted on the Smith chart represents the admittance of the load. That's this dot right here. So picture yourself standing at the end of a piece of coax nearest the load. As you move along the coax away from the load, you are moving toward the signal source, the generator, or the transmitter. When we move in this direction, we traverse the Smith chart in the clockwise direction. Starting at the second dot you placed on the Smith chart and moving clockwise around the SWR circle that you drew, follow this around until you find the first place where your SWR circle crosses the G equals 1 circle. And so we have the G equals 1 circle here, and we have our SWR circle here. We have our admittance here, and we're traveling clockwise around until we come to a place where the SWR circle crosses the G equals 1 circle. We place a dot in that location. And now we can read the new admittance at this part. It's really easy, the real part, because the real part is going to be equal to 1.0. The reactive part is what takes a little bit of guesswork. We have to kind of use our calibrated eyeball here. We got this line right here, which is 1.6. We have this line, which is 1.8, which makes this one in the middle 1.7. And we kind of eyeball this out and say, well, it's about halfway between the two, so we're going to call that 1.65. And because we're in the southern hemisphere, that'll be a minus 1.65. So our admittance at point A is going to be equal to 1 minus J 1.65. The next thing we have to do is locate this new admittance in the wavelength realm, and we do that by drawing a line from the center through this new admittance at A all the way to the edge of the Smith chart. And then we want to read this new number off the edge of the Smith chart to find out what kind of position it's in. So we have 0.31 here, 0.32, 33, and this just happens to fall almost exactly on 0.32. So we're going to call this wavelength at A equal to 0.32 wavelengths. Now we have to calculate the length of our admittance transforming coax. So with our lambda sub load equal to 0.224 wavelengths, and our lambda sub A equal to 0.32 wavelengths, we can calculate the length of the admittance transforming piece of coax. The first step in calculating the length of our impedance or admittance transforming piece of coax is to calculate it in terms of wavelengths. This is the electrical length in wavelengths, is that what we're trying to do here. Now, we've already established at this point, we know what the lambda sub load is by seeing where we come out here onto the edge. I have two different instances shown here. And we have already moved clockwise from this point around this to the lambda sub A point. So we have a value for lambda sub A. We have a value for lambda sub load. And now what we need to do is find out what the distance is between here and here, or here and here, depending upon where our lambda sub load ends up. Now, if in the process of moving around clockwise here to get to that first point where your SWR circle crosses the G equals 1 circle, if you've crossed this 0.0 meridian here, which is also, if you remember correctly from the tour, that's the same as a 0.5. If you've crossed that point, we have to do this in two pieces. First, we have to find out what the distance is here. Then we have to find out what the distance is here. Well, from 0 to here is this. So we know that this distance from here to here is the same as our lambda sub A. But what about this? Well, that's this part. 0.5 minus lambda sub load will give us this distance, and then we add it to this distance to give us the overall length of the coax. Now, if on the other hand, you did not pass 0.0, let's say your impedance is sitting here and you've moved from here to here, you've not passed this part. Now we're just talking about this portion here, and that's just simply lambda sub A minus lambda sub load gives us the electrical length of our coax in wavelengths. Now in our particular case here, we did not pass the 0, 0 mark because we were over in this area over here, and we moved from this area down this way and came to a place here. So we have one here and we have one here. So in our case, because our lambda sub A is equal to 0.32, and our lambda sub load is equal to 0.224, and we did not cross there, so our lambda sub coax is going to be just 0.32 minus 0.224, which comes out to be 0.096. 0.096. Well, we have a hard time measuring coax in terms of wavelength. We need something that we can put a measuring stick to and measure. And that introduces the next thing of translating this number right here into a physical length with real physical coax. Because the physical length of a wavelength changes with the frequency of interest, we have to include the frequency in hertz. And as I said in video number 3 of the series, the physical length of a wavelength in a transmission line depends on how fast that signal can travel down the transmission line, and that is determined by the velocity factor of the coax and the speed of light in inches per second. And so the equation comes out, the physical length of our piece of coax is equal to the electrical length of the coax in wavelengths times the velocity of light in inches per second times the velocity factor of our coax, all divided by the frequency in hertz. And so in our particular case, we have a velocity factor of 67%, a frequency of 146 megahertz, an electrical length of 0.096 wavelengths, and the speed of light is 11,802.853 times 10 to the 6th inches per second. And so we come out with the electrical length 0.096 times the speed of light 11,802.853 times 10 to the 6th times the velocity factor, which is 0.67, all divided by 146 times 10 to the 6th. Now, because we have a times 10 to the 6th on the bottom and a times 10 to the 6th on the top, we can just scritch those out, and we're just left with the 0.096 times the 11,000 number times the 0.67 divided by 146, and we get a physical length of our impedance transforming coax, our admittance transforming coax of 5.2 inches. Now we get to turn our attention to the stub. We've already found that the admittance at point A is equal to 1 minus J 1.65. Now what we really need is the admittance at A to be equal to 1 plus J 00, because that would be a perfect load, we would have a 1-to-1 SWR. Now, in the second video in this series with admittances in parallel, the rule is that the total admittance is equal to the sum of the admittances in parallel. If y sub stub is equal to 0 plus j 1.65, and we have ya equal to 1 minus j 1.65, then we would end up with the total y is equal to 1 minus j 1.65 plus 0 plus j 1.65. 1 plus 0 is 1, minus j 1.65 plus j 1.65 is 0. We got exactly what we want. So now we need to plot this on our Smith chart. Now the inside part of the outer ring of this, as I pointed out in the Smith chart tour video, is the G equals 0. And that's what we want, G equals 0 here. We notice that this is a plus, so our admittance that we're plotting here has got to be in the northern hemisphere, and now we have to find 1.65. So we go along the edge here, we see 1.4, 1.6, 1.8. This has got to be 1.7, and halfway in between gives us 1.65. So now we have plotted our stub admittance. The next thing we do is we draw a line from the center here through the stub admittance that we just plotted all the way to the end, right here at the wavelength rings, so that we can locate this admittance in the wavelength realm. Next, we read the wavelengths off of the edge here. Again, we take out our calibrated eyeballs, and we see we have 0.16, 0.162, 0.164, 6, 8, so on. So this is about 3/4 of the way between 0.162 and 0.164. So we're going to call that 0.1635. The wavelength of the stub is 0.1635 wavelengths. Now we have to move clockwise from the open, because remember we have an open stub here, and according to what you learned in the video on the Smith chart tour, the open for admittances is over here on the far left-hand side of the Smith chart. And so we are moving from the end of that stub clockwise around, because we're moving toward the admittance that we want, which is closer to the generator. So we're moving toward the generator clockwise around until we get to here. So with the wavelength of the stub equal to 0.1635, that's where we're going to, and the wavelength of open equal to 0.00 wavelengths, we can calculate the length of the stub coax, which eliminates the reactive portion of the admittance at point A. The first step, just like with the admittance transforming piece of coax, in calculating the length of our stub is to calculate it in terms of electrical length in wavelengths. So here is our stub right here. We're moving from the open. Now we're thinking about this now. We're standing there at the open end of that stub, and we're moving toward the T. So we're moving toward the generator. We're going to be going clockwise around the Smith chart. The open is over here on the left, and so we are moving in the clockwise direction from y equals 0 plus j0, the open, and we're coming to here. So we have already read the lambda sub stub is equal to 0.1635 here. So we're looking to figure out the distance between these 2 points. So you have lambda sub coax, or r stub, is equal to the stub here minus the wavelength associated with the open, which is 0. So you end up with the lambda sub stub minus 0. Well, that's the same thing as the lambda sub stub. So our stub piece of coax needs to be 0.1635 wavelengths long. But like before, we need to figure that out in inches so that we can get out our handy dandy ruler and actually measure a physical piece of coax. Well, the process of calculating the physical length in inches of our stub is exactly the same as we had for the admittance transforming coax, so I'm not going to go through every little step. The only thing that changes in the midst of all of this is this number right here, the electrical length of the coax in wavelengths, and then down here, this is the only number that changes in this whole equation here, just here. So we do exactly the same thing as we did for the admittance transforming coax, and we multiply the 0.1635 times the speed of light in millions of inches per second times 0.67, which is the velocity factor of our coax, divided by 146 million cycles per second, and we end up with a physical length of coax of 8.86 inches. We have just finished working through the process of creating a parallel stub match using an open stub. The incoming impedance was 11.65 minus J8. That gave us an SWR of 4.44 to 1. The outgoing impedance was 50 plus J0, which is an SWR of 1 to 1, just exactly what we want. To accomplish this task, we used a piece of coax that was 5.2 inches long to transform the load's admittance to one which had the real part that we liked. We then added a stub of coax 8.86 inches long in parallel whose far end was open. If you find this video helpful, please click on the like and subscribe to the channel. In the next video, I will be creating a real-life stub match to match my purposely horrible load that has an SWR of 5 to 1. I will be creating a parallel stub match with a shorted stub. I will be talking about measuring your coax for your stub match, trying to cover the practical aspects of the process, as well as stepping through the design process. In the meanwhile, thank you so much for watching. Toodle-oots.